Hi guys, welcome back to Data Every Day. Today we'll be looking at a data set of COVID-19 healthy diets. Well, what that means is uh, it's going to be a data set of countries and the percentage of food intake that belongs to different categories. And we're going to be trying to use those to predict whether the mortality rate is high or low. So let's get into it. I have the task for today here, predicting COVID-19 mortality based on diet. Given data about various countries and their daily intakes of different food groups, let's try to predict whether a given country will have a high or low COVID-19 mortality rate. And we'll be using TensorFlow artificial neural network to make our predictions. So I'm importing these standard libraries, NumPy, Pandas, Plotly, and standard scalar and train test split from sklearn for pre-processing. And then we'll import TensorFlow for our actual model. Alright, so I'll load that in, and then we can load in the data with pandas.readcsv. We can get the file path right here, and the one we're using is actually food supply quantity kilograms data.csv. So paste that in, take a look at it, and here's what we were seeing before. But right before we do anything, notice there's a dot 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 here. That means we're not seeing all the columns. So we could open the console and just write pandas.setOption max columns equal to none. Now we can see all of the columns, all 32 features. 31 features, I should say, or potential features. So this is what we're going to be using as our prediction. And I'm not going to have it, I'm not going to do a regression on this. I could, but I figured out, why don't we see if we can split this data into high and low, and see if we can classify if a country will have high or low mortality based on the food intake. So some things to notice: this unit column is not going to help us, right? Actually all have the same unit. There's one unique value, so we're just going to drop that right off the bat. But first, let's just take a look at some preliminary information. So see, most of these don't have null values. We're only working with 170 examples. So there's a sum here at the bottom that have some null values. Additionally, there's only 3 object columns: unit, undernourished, and country. Everything else is numerical, so there's minimal encoding that has to be done here. Let's drop unit. So let's start pre-processing, and let's say data equals data.drop, and it's called unit all except population. So paste that in, and axis 1. Okay. Then we're going to deal with the missing values. Alright, so data.isNA will give us all the null values, and then we sum across the rows to get the number of null values in each column. And we can see we have 3 here, 7 here, 9 in these 3, and 12 in active. So because most of this is numerical, we can just impute the missing values to be the means of the columns. However, there is this problem of undernourished. Okay, and undernourished is actually an object column. Now if we look up here, it looks like it's numerical data, right? But these are actually strings, and there must be something in here that is not a number. So we'll come back to it, but first I'm going to fill in the missing values for all of the other columns. So for column in data.columns, so for each column, if data.dtypes subcolumn is not equal object, So if we're dealing with a numerical column, and data.isNA.sum subcolumn is greater than 0. So in other words, if it's a numerical column and it has some null values, we're going to fill in the missing values, fill in A, with the mean of that column. And we're just going to set the column equal to be that. Alright, and if we run that, we run this again, you can see all the missing values that have been filled in with the mean, except for undernourished, which is this one problematic column that has an object data type. So now let's say, okay, dealing with the undernourished column. Okay. Let's take a look at why we have a problem. So if we try to, if we take undernourished, and if we try to convert it to a float, so as type numpy.float, we'll run into an error, and it says, uh-oh, could not convert string to float less than 2.5. So that's a problem. There's basically it's all numerical except if the value is under 2.5, it just gets encoded as a single value, which is a string that says less than 2.5. So there's a few ways we could work around this. We could just drop the ones with 2.5, but we should take a look. So I'm just gonna data sub undernourished dot value counts. Aha! You can see that less than 2.5 actually makes up for 44 examples. And we only have 180 examples. So we can't just drop 170. We cannot just drop 44 of those, right? We're going to have to think of something more creative. So notice that we can actually discretize this variable. So right now it's a continuous variable, but we can bin it. We can take the quantiles of this the distribution of the data and separate them into bins, right? So let's try this. If we have data sub undernourished equals less than 2.5, you can see, and let's sum that to see how many we have. It should be 44. Sure enough, 44. So this right here is actually a list or a series of all the. It will be false if it's not 2.5 and true if it is. And we can't actually see the ones that are less than 2.5, but those will be true. So if we say not equal to, then we'll only have false when the data is not less than 2.5. Sorry, when it is less than 2.5. So this basically any series of true and false values we can use as an index in a data frame or a series. So right here we're going to actually say data.loc using these as the x index, as the row index, and undernourished as the column that we want to look at. This is all the values in undernourished that do not have less than 2.5. And you can see it has length 126. And 126 is just 170 minus 44, right? So this is all of the ones that are numerical, essentially. And what can we do with that? Well, we can fill in the missing values and discretize it. So what I'm going to do is call this something new. We'll call it undernourished numeric. And that's just going to be the series of values in undernourished that are not strings. And yeah, we could just take a look at that. It could just be what we have. And we can use now a pandas function called qcut. It's a quantile cut, and we're going to cut undernourished underscore numeric into 4 quantiles. Okay, and we'll give them labels 1, 2, 3, 4. And the reason I'm not starting at 0 here is if you can make a guess, I'm going to use this as the 0 quantile. I mean the 0 bin. So, and we have problem unsupported operand type. String. Okay, let's try this. Wait, what's wrong here? Yes. Right, these are actually still strings. I have to make this a float. As type numpy.float. If we're going to be performing a quantile cut on it, we have to make sure they're actually numbers first. So run this. Now it's the same as before, but it's actually floats now. Now we'll do that, and you can see it will be converted into its individual bin. For example, if I don't use the labels, you can see it shows the range that it's been set into. And there's only 4 of these. There's bin 4, I think bin 1, bin 2, and so on. But I'm going to keep the labels in there so you can see. However, before I do that, I want to fill in these missing values. Because if I fill them in after I bin them, we're going to have, it won't be, it'll become continuous again, right? So we're just going to do that first. Undernourished numeric dot fill na. And we're going to fill it with undernourished numeric dot mean. And that will fill in all the missing values with the mean. And we could say, well, undernourished numeric now equals this. Okay, now if we cut it, we have everything in a bin and no more missing values. So this will just be our new undernourished numeric. Okay. So now, yeah, let's look at it. This is good to go. However, okay, let's see. Let me just put these on one block. And then, we still have the problem of the other values in undernourished. So data sub undernourished looks like this. Let me just rerun all these so I can. Okay. So we haven't actually set these yet, so we still have the old values here, but these are essentially taken care of. However, this you can see the length here is 126, but we retain the old indices. So when we want to set these indices, it'll leave the string values alone, and it will only change the ones for which we have indices in this one. So I think what we'll do is first we'll apply a lambda function to this. So data sub undernourished dot apply lambda takes in an x and returns 0 if x is the string we're looking for. And we're saying 0 here because that's the bin that we want for this for the 44 examples, right? We have 1, 2, 3, 4 here, and then 0 will be less than 2.5. And I just realized something. We have 44 examples that are less than 2.5. Maybe we shouldn't do 4 bins. Well, we have 170 total. 44 of them are a single type. That's 25%. Aha! So maybe we should do 3 bins. So we bin the rest of the data into 3, and then we'll have that one. They'll have of about equal size, right? So I think let's do 3 bins. Right, take off that 4th one, and now rerun the whole thing. Now it's been binned into 3, and 0 is going to be the 4th bin and that's going to be if it's less than 2.5. So the reason that I got an error is I have to specify else will be x. What that means, if we'll make it 0 if it's a string that is less than 2.5. Otherwise, we'll keep it the way it is. So if we look at that, we can't actually see how it was changed, but it worked. So data sub undernourished equals this. Alright, let's take a look at data. And okay, undernourished still has not been, we have not applied it yet. So all we have to do is say data.locate undernourished numeric, that's this thing up here, this thing right here, right? Undernourished numeric dot index, and that's going to give us the list of the indices here. So we're only going to index our data, this thing, at the locations where we have numerical values. And then for the y, we're just going to target the undernourished column. And now this is going to be equal to undernourished numeric. So you see what we're doing? Anything that has a where is it? Undernourished. Everything that has a numerical value is going to take on a new bin value, and everything that doesn't already has a 0 there. Oh, I probably did this in the wrong order, right? Because 0, no, it wouldn't matter, but I think it's better in this order anyway. So let's do that. Let's run this. Okay, I'll just run it through. And we can look, now all these should be properly binned, just to be extra sure. Data sub undernourished undernourished dot unique. Looks like this. Fantastic. And if we look at the value counts, you can see they're all of roughly the same size. So that is fantastic. That's great. We have effectively transformed this column into a usable column without just dropping it, right? So we're retaining information. That's always good. Okay, so what next? That was a lot for one column, right? Let's try, now we're going to do feature selection, feature and target selection. Okay, and I guess, would this be considered pre-processing? I guess it would, so I'll do that. Alright, we're going to drop all the columns we don't need, essentially. Now, country, we actually don't need, because it's unique for each one. Each one of these examples is a different country. So, data equals data.drop country. Axis 1. Let's see what else. All these are very useful. Just actual food groups. And these is useful. But we actually look at this. We don't want to be using the number of confirmed, or the percentage of confirmed cases in the country. And why is that? Well, that's not really what we're trying to do here. That's not our task. The task we're trying to do is predict it based on diet alone. So undernourished and obesity still count as diet, essentially, but confirmed cases and how many recovered and how many are actively infected do not help us, right? And it's sort of cheating to use those if we're considering the task that we're going for. So what I'm going to do is just drop those as well. So the columns we're dropping here is going to be confirmed, recovered, and active. Okay, so we drop those. Take another look at this. We now have 27 columns, and we just have this one thing that we're going to try to predict. And I said earlier we're going to bin that as well. We're going to discretize the deaths column so that we can just know high or low instead of regressing to find a continuous value. Although we absolutely could do that if we wanted to. So we can use the qcut function again, this time on the deaths column, and we're going to have two bins with labels 0 and 1. Alright, so that will convert high values to 1 and low values to 0. And I can get the value counts to show that we actually have even numbers in each one. So high or low is totally relative to the distribution of this data. Okay, so let's actually set the deaths column to be the quantile cut. So data sub deaths, just going to equal this thing, not the value counts. Right. Okay, so we're ready to split and scale. Splitting and scaling. Now we'll take a look at our data. Everything is in numerical form now, and deaths is either 0 or 1. That will be the column we're trying to predict. So y equals data sub deaths. X is going to be data.drop deaths. Axis equals 1. Alright, we'll make a scalar object using the standard scalar from sklearn. And x is going to be scalar.fitTransform x. That'll fit the scalar to our data, transform x, and then store it back in the variable. Okay. And then we're going to split it into a train and test set. X train, x test, y train, y test equals train, test, split, x, y. We'll specify a train size of 80%. Alright, now we're ready to train. So let's look at the shape of our x. Okay. And we have 26 features and 170 examples. Okay. Another thing, we can use accuracy as a metric here because we have equal number of examples in each category. However, we may also want to use another metric that will be more. It will be better at describing how well we're doing within each category. So I think we'll use the area under the curve, under the receiver operating characteristic curve. So let's start building our model. We can have our input layer will be tf.keras.input, and we'll specify the shape. This will be the length of our feature vector, which will just be 26. And then we'll have two hidden layers. The first, they'll look identical. tf.keras.layers.dense with 64 activations and an activation function of ReLU. Here we'll pass in inputs, and we'll copy the same thing for the next hidden layer, but here we'll pass in x. Then for output layer will be tf.keras.layers.dense, and only a single output with a sigmoid activation. And this will be the probability estimate that a country has high COVID mortality. Here we'll pass in x as well. Model equals tf.keras.model. Inputs equals inputs. Outputs equals outputs. Alright, then we'll compile our model. Optimizer is going to be atom. Loss is going to be binary cross entropy. And the metrics we'll use will be accuracy and tf.keras.metrics.auc. Name AUC. Alright, then we'll give it a batch size. Let's say 64. Number of epochs, we can start training with 100. And then let us store our model's fit history in a history variable. So history equals model.fit. I'm going to train it on X train, Y train. Give it a validation split of 20% and specify the batch size and epochs as we have above. Alright, and then I'm just going to turn off verbose mode so that we don't clutter the notebook. And while that trains, I'm going to start visualizing the results. We're going to create a Plotly figure to show the performance over time. So fig will equal px.line, plotlyexpress.line for a line chart. And we're going to draw our values from history.history, which will be the history attribute of this. And that thing has two dictionaries, one called loss and one called val loss, which will give us the training loss and validation loss at each epoch. So for labels, on the index, which is the x-axis, we'll call it epoch. And on the y-axis, which is the value, we'll call it loss. Then we'll give it a title. Let's call it training and validation loss. Alright, and then just fig.show. And this is pretty much what we expected. We start off, both losses are going down, and the training loss continues to go down, but at some point the validation loss starts to go up. And that's just because the model gets better and better at memorizing the dataset, but starts to get worse and worse at generalizing to new examples. So we're overfitting at some point. And to find that point, we're going to call the argmin. We're going to find the argmin of the validation curve, which would just be not the minimum value, but the x value for which we have a minimum. So it will be the epoch that gives us the minimum validation loss. So history.history sub val loss, and that's 13. Alright, so at epoch 13, this is the minimum loss. And this starts at 0, so we're actually going to train for 14 epochs. Alright, run that. Run this again. Now you can see it converges very nicely. Still 13. And we can evaluate our model on the test set. X test, Y test. And we end up with an accuracy of about 55%. And an AUC of 0.6. So, not very good, right? That is not great. Now, it is important to note that our test set is extremely small, right? Look at the size of it, the length of Y test. There's 34 examples. So if we got 34 hard examples, we might have a lower accuracy. Whereas if we have 34 easy examples, we might have a higher accuracy. It's just not enough. So this might be actually a better model than we think. We don't know though. Why don't we try resplitting? And the thing is, this function actually shuffles the data. So we could specify a random state in order to get the same shuffle each time, but let's see what happens if we use a different shuffle. So we shuffled it differently. Now we're going to train it again, and now we're going to evaluate it again. Before we had 55% accuracy, now we have 58. Okay, it didn't go up that much. I still think this model really isn't doing what we need, but it's better than a random guess, right? So there's some amount of information in this data set that contributes to predicting whether or not a country has a high or low mortality rate for COVID-19. And yeah, I think that will sum up today's video. I hope you liked it. If you did, make sure to subscribe and hit the bell, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.